So hello everyone, my name is Tuan Nguyen. I'm from University of Turku, Finland. So I'm here to present my paper, Detection of Epilepsy Seizures based on deep learning with attention mechanism. The outline of the presentation today includes introduction and motivations, and then I will present the methodology for epileptic seizure detection using a single EEG channel. Then I will present the experimental results and performance evaluations. And finally, I will conclude the work and also present the future work. So epilepsy is a non-communicable neurological disease. And epilepsy is a central nervous system disorder. The brain activity of a person with epilepsy can become abnormal, causing seizures or uncommon physical behaviors. Epilepsy can occur and affect anyone, regardless of the ages, genders, or human races. Although epilepsy is not a contagious disease, but epilepsy cannot be underestimated because epilepsy can lead to sudden temper, loss of awareness, or disturbance of movements. The people have epilepsy often have a 3 times higher risk of premature death than normal healthy people. For example, an epilepsy seizure can occur at certain time which can lead to the serious consequences such as a sudden falling or drowning or the car accidents. Epilepsy can be categorized into sudden and long-term recurrent epilepsy. The sudden epilepsy means that a patient will have a seizures unexpectedly in random intervals. Long-term epilepsy means that the seizure of the recurrent epilepsy occurs repeatedly in some expected ways. So therefore, it is more difficult to detect or to deal with the sudden epilepsy than recurrent epilepsy. But both are not good for health, especially they can negatively impact on the patient's quality of life. Fortunately, epilepsy seizures can be controlled. If the epilepsy is detected, diagnosed, or treated properly, based on the statistics, more than 70% of people having epilepsy could avoid seizures if they have used anti-seizure medicines. And currently, there are 2 most common predictors of the seizures. The first one is a documented etiology of the seizure, and the second one is the monitoring the abnormal electroencephalography EEG. So as usual, when the data is monitored and then it will be recorded into some paper forms, and specialists, they need to use their knowledge to analyze the EEG waveforms. But this can cause some limitations. For instance, such as like high cost, lack of like specialists, and may not be accurate. So it is required to have an accurate or automatic detection of epileptic seizures. So that's the reason we would like to propose our advanced approach for automatic detection of epileptic seizures based on the monitoring ECG. So next, I will introduce the methodology for epileptic seizure detections using a single EEG channel. So the proposed approach consists of three main stages, including feature extraction, classifier training, and classifier classification. So before feeding any data or input into the neural network, the data need to be pre-processed, and similarly, in our case, we also pre-process the ECG by applying pre-processing techniques such as data normalization, data fitting, and data resampling. So it is noticed that the raw EEG data from different ECG measurements or data sets, they can have different frequencies. However, the input for the model, for the neural network model, should be uniform. Therefore, we have to apply data fitting. And why we need to apply data resampling? Because as we know that the EEG have different distributions. For instance, like different components, such as the alpha wave is from 8 Hz to 13 Hz, and beta wave is from 13 Hz to 30 Hz. So, and as usual, the main components of the ECG is from the 0 Hz until 160 Hz. So it is perfect if we can use some systems which collect the higher sampling rate data, such as 300 samples per second or 300 Hz. But however, when the system use very high data rate, high sampling rate, it goes like the last input for the neural network, and it will cause some problems in the training phase, such as the resources utilization. However, we would like to target the edge systems where the edge servers or the clock servers are terms of the resource constraint. So it means they have limited resources such as limited battery, limited computational capability, limited memory. Therefore, we need to find the proper sampling rate for our EEG. So we try different sampling rates from 43 Hz until 173.6 Hz. So, however, thanks to the pre-process by the data set, such as in terms of like noise removal, so the results we have from different sampling frequencies are almost similar. So almost similar. So that's the reason we try to apply the not very high data rate, which can be suitable for action for systems to provide a real-time results. And the proposed neural network shown in the figure 1. So in the figure 1, you can see that the proposed neural network structure has the spatial modules such as inception modules, residual modules, and attention modules. So these modules are core of our network. So these modules will be explained in the next few slides. So we customize the attention module. So the attention modules can be split into attention trend and a skip connection. In an attention trend, the output from the previous modules, such as the residual module, is an input of the trend. And we apply the bottom-up and top-down structures described by Ziyu to achieve the same size of attention march. So this structure imitates the feed-forward and feedback attention procedures, so which is similar to the feature selection process of the feature pyramid network. And you can see the modules here. We have two main phases, like encoding and upsampling. And next will be our residual block. So the basic residual block is shown in figure 3, and this block has two weight layers. So the block can be presented with the formula y equal to fx plus x, as here in the figure. And several residual blocks can create the residual module. So here we show our residual module, which is made from 3-stage residual blocks. So the first one, the second one, and the third one. So to extract the useful ECG features from ECG data, so we apply the inception module. So the inception modules consist of several kernels, such as 1 by 3, 1 by 5, 1 by 7. So these are used for the basic convolution layer to avoid the patch alignment issues. So before these kernels are applied, the kernel 1 by 1 is applied for reducing the computation. So the result of the X convolution is concatenated for forming a multi-dimensional tensor, which will be used as an input for other modules. And next, we will show our experimental results. So we use a cross-validation method and two different datasets, such as a Bond dataset and the Children's Hospital Boston, Massachusetts Institute of Technology dataset, is named MIT dataset, to evaluate the proposed neural network structures. So in the cross-validation method, a small set of data is fed into the structures, and the model's performance is estimated when it applies the predictions on unseen data. The overall procedure of the cross-validation method with the K-phone described is the K-phone having 4 main steps, such as random shuffling on the data, randomly selecting data into the K categories, using each category as a testing set to evaluate the method, and finally summing up the performance of all models. So in our experiments, we use the 10K phone, and the metrics we focus is accuracy, sensitivity, and specificity. So we compare our results with the other step years results, applying the same bond dataset. So as you can see from the table 2, we got better results in terms of accuracy, sensitivity, and specificity in most of the cases. And it is noticed that in cases such as Ziyu S, NFS, ZS, or FS, we have very good results because from a data set it is easy to distinguish between the tasks. However, in case of the 5 subclasses such as the last case Z, O, and FS, the result is not high because the data of the eye open and eye closed is not much different. And the second experiment we apply with the MIT dataset. So the collection of the raw EEG data is between 1 to 4 hours, and the sampling rate for this case is 256 Hz. So ECG signals of each patient contain 23 channels. So in these papers, we only use the ECG channels of FP1 to FP7, F7, T7, and so on, to build our own EEG dataset. So as you can see from the figure 5, so our results are almost similar to the other approaches. And in some cases, we have the better results. And however, in some cases, we don't have the better result, but the result is quite similar. And similarly for the task zone ZONFS, so we also have very good results compared to others. However, it is noticed that in case of the task ZONF and S, the results are not good and similar for others. However, we still have the better results than other state-of-the-art approaches. But however, it's our limitation. So the model needs to be refined to improve. Improve especially for the task ZONFS. And finally, we will conclude our work. So we propose an approach based on advanced deep learning neural networks for automatic detection of epileptic seizures with a single EEG channel. So the approach could achieve 98% of accuracy, 99% of sensitivity, and 98% of specificity for a single EEG channel for many cases from the applied datasets such as the Bond and MIT dataset. But however, in the future, we will apply the real-time monitoring approach. So we will collect the real-time EEG from the volunteers and the patients, and then we will use it to fit it into our models and evaluate it. And in the future, we also develop There are another approach for multiple channel EEG. The new approach will be based on the singular channel EEG. Thank you very much for your listening. If you have any questions, we are happy to answer.